Okay, so I would like to thank the organizers, especially Philip Gill, for organizing this conference and for giving me the opportunity to speak here. You know, I am just learning Bruhat-Tits theory, maybe in a different way, and that's what I want to present here. And also, I would like to thank Philip for giving me his better room here. So, yeah, so that was nice. Thanks a lot. And Bertrand Remy for introducing Bruhat-Tits theory over fields, maybe maximal unramified extension for me. Whenever the group is quasi-split, the Bruhat-Tits theory is easier to explain, and he did it very well, so I would make use of it. So let me fix some notation. I will always denote by K a field given with valuation, real valued valuation omega, and after a little while I will assume that omega is discrete. You know, some people may be interested in non-discrete valuations, but I have never worked with them, though I feel that many of the results I will mention should go through for non-discrete valuations. But you know, I cannot be sure. Now, this field will be assumed to be henselian always, which means that for any finite extension of the field which we will work, there will be a unique extension of omega, the valuation. Another way to say the property henselian is that if I take the ring, which I will denote by O, the ring of integers, then if you have set of nice equations which you can solve over the residue field, which I will denote by F, the residue field, so if you can solve the equations over F, then nice equations, you can solve them over O. You know, in particular, if you have a smooth variety over O, and you take the special fiber, which means going to F, and if there is a point over F, you can lift it to point over O. So that's the henselian property, and without that, I cannot work. Now, capital K will denote a maximal unramified extension. So this is an infinite extension, but we will not worry about that. It's a limit of finite extension, so valuation will extend, and you will still have. And the ring of integers here will be denoted by a bigger O. This will be a small o, and this will be a bigger O, ring of integers. And the residue field will be denoted by capital F, the residue field. And the residue field, it will be separable closure of the small f. Now, to avoid complications, I will assume just in these talks that F is perfect. So the P power map is an isomorphism where P is the residue field characteristic. Okay. On the other hand, in the paper which I wrote on this topic, I'm not assuming because of Sayre, I remove the restriction that f is perfect. So as long as you have a theory available over capital K, you will have theory over small k. So the descent is possible even without assuming that the field is, residue field is perfect. So even for imperfect field, but the complication is that when you take special fibers of the Bruhat-Tits group schemes, then special fiber means the fiber over the finite residue field, then you cannot talk of its unipotent radical because the field is imperfect. So its unipotent radical, only a part will be defined over the base field. So when you divide by it, you will have to look at the book on pseudo-reductive groups, and I don't want you to purchase it. So I will restrict myself to perfect fields. But everything can be done perfectly well without assuming that, but you will need to know the theory of. Okay, so that's one restriction which I am imposing, even though the symbol f might say that f is finite, but it may not be. The residue field I am assuming is perfect, but not necessarily finite. So if you want to work with complex numbers and Laurent power series over complex numbers, that's allowed. And many of you do geometric Langlands, so you may welcome that, yeah? So, okay. Now, G will always denote a reductive, which means connected, reductive K group. Okay, and now for a affine variety X over K, what is a bounded subset of xk bar or any field extension? So, a subset B is bounded, yeah, just a definition. If for every function, algebraic function f on the variety X, fb, b varying over b, so omega fb is bounded below. For each function, it's bounded below. You see, negative values of omega mean that the number is becoming large. And positive value of omega means the number is shrinking to 0. So you don't want the numbers to increase indefinitely. So boundedness precisely means this. So we are just demanding that for any function f, the value as you vary the points to, on B, they remain bounded. Bounded, yeah, so they don't keep increasing, and which means that the valuation is bounded below. Okay, so that's one thing. Now I am going to describe, you see, all this valuation of root datum and so on was given in the case of quasi-split groups to construct Bruhat-Tits theory. And I find that to be quite, simple in some sense, because you have, for a split group, the Chevalier basis, which allows you to parameterize root groups. Pardon me?
What kind of functions is it? Continuous function or regular function?
No, these are functions from, Kx. So f belongs to, even K bar x. So just the algebraic function. globally defined algebraic functions. Okay, now you see the root groups for Chevalier groups using Chevalier basis are, so U sub A is root group, these are one-dimensional, and there is a canonical parameterization once you fix the basis. Suppose you are working over capital K, then you have canonical parameterization up to plus minus 1 of UA with K, and you can use the evaluation now to get inside G union infinity in case of discrete valuation. So, this gives you what Bertrand said, valuation of root datum. But if the group is quasi-split, not split, then Steinberg had made an analysis of what you can do with the Chevalier basis. So he will take a splitting field K prime over K, degree 2, degree 3, a degree 6 extension for absolutely simple groups. So it's a very small extension. And Galois, so that will be splitting field. And except for A to N, as Bertrand remarked, except for this root system, you will have now the relative root groups, namely root groups over K, and the group is not split over K. If it was split, you already have the theory. So if the group is not split, then you will have to go to a K prime splitting field, fixed splitting field, and then you see on the relative root system comes from the root system over K prime, and the Galois group operates on the root system over K prime, and each Galois orbit of roots upstairs gives you a root downstairs. So the Galois orbit of a root upstairs may, even though the field extension here is degree 2, may fix that particular root, and in that case, UA will be one-dimensional. But if the root upstairs has in the orbit 2 roots, then you will get restriction of scalars of a degree 2 extension, which means that the corresponding UAK will be, in that case, isomorphic to a quadratic extension K prime. So in case of relative roots, except for A to N, there is no complication. You always have the parameterization of UAK by a suitable finite field extension of K contained in K prime. And so if trial T D4, you will get a degree 3 extension for the short root, and for the long root degree 1 extension, namely K. So that's the way things work. Another thing which, and then for A to N, you have additional complication because the root group, which is corresponds to multipliable root, as Bertrand said, A and 2A can simultaneously be roots, and such roots are called multipliable. A and 2A simultaneously are roots, and for multipliable roots, the corresponding root group is 3-dimensional and it's not commutative. But this still allows you, with a little more analysis, to put a valuation. And this is done in appendix of Bruhat-Tits 2, and also in my paper with Raghunathan, which appeared a little before Bruhat-Tits 2. So, we had to analyze that because we didn't have access to Bruhat-Tits 2. So we do the quasi-split case in detail in that paper, since we didn't have Bruhat-Tits 2. So in any case, that requires some commutator computations and so on, because to check the root datum axioms, as Bertrand this morning showed us, you have some computations to do with root systems and commutation relations between root groups. Another thing which I want to add to what he said was affine root systems. So if the group is split, the affine root system which takes into account the valuation, and suppose the value group is G, then the affine root system is just phi the root system multiplied with G. Because each root group has valuation taking values in G. But if the group is not split, then as I said, the root system, the relative root system, the root groups may be between K prime and K. So so suppose a particular root group requires a degree 2 extension. There are two roots lying above that. Then for the corresponding root group, the evaluation will be in half G, because you are extending the evaluation to a ramified degree 2 extension, so you will have half G coming up. And in case of trial D4, you may have 1 by 3G. So you will have that kind of evaluation. So the general recipe which sometimes people use without even knowing is that the affine root system, this is called the absolute affine root system because I am working over maximal unramified extension. So the affine root system is given by the following very simple recipe. And then you can read while group also, affine while group. So the affine root system psi is the affine root system is over K. So it's given by the following recipe. If G splits over K, it is just the ordinary root system multiplied with G, and this you can call whatsoever name you want to give. So if phi is of the type AN, you might call it AN tilde. Okay? Now, if G does not split over K, so on the other hand, if G does not split over K, then what do? So you see, let me give you one simple example. So suppose I have type Dn, and the group does not split over K, means that these two roots are permuted by the Galois group of K prime over K. So these two roots collapse and they give you a short root. So from Dn over K prime, you get Bn minus 1 root system. Okay, so that's the root system of the same group over K. For example, you might take a quadratic form in n minus 1 hyperbolic plane, direct sum with norm from a quadratic extension. So that will be a quadratic form which is not split over the base field, but over this quadratic extension it becomes split. So in such a case, your relative root system over K, the group is quasi-split, the relative root system is Bn minus 1. Okay, and in this case, what you will do is, you will take the root system below, which is not Dn but Bn minus 1, and take the dual root system, and then take the corresponding affine root system. and then take the dual. And that's the psi. Okay, so as a simple exercise, can you tell me what would be the affine root system in this case? You see, you have to reverse the arrow because I'm taking the dual, and then you have to take the corresponding usual affine root system, and then you have to reverse back the arrow. So let us do that just for once in life. So in case of Bn minus 1, you have to reverse the arrow. So you will get the root system which is called Cn minus 1. And what is the corresponding affine root system? The usual one. So you know this is long root, these are short roots, so you always attach a long root. So this is the affine, Cn minus 1 tilde. So that's this root system. You understand? So in Cn minus 1, you always attach the long root. But now you have to dualize. So in case of this, you will get back this. Oh, sorry, I didn't put the arrow in reverse. So you will get this root system. So this will be the affine root system for the group Dn, which is a quasi-split but not split over maximal unramified extension. Okay, and you see this, this tells you quite a bit about So this tells you quite a bit. The symmetry here is multifold. So, the symmetry of this diagram has degree 2 symmetry. And so you can have over the base field, these symmetries give you what are the possibilities for the group over the given base field. So the Galois group, so there is a Galois group operating here. This is an infinite Galois group, but of course, on a finite diagram, it operates through a finite group. And this, this diagram has only one non-trivial symmetry. This root can be mapped to that and so on. So this diagram has only one non-trivial symmetry. So this infinite Galois group operates through a quotient of degree 2, which means that whatsoever happened over capital K is already realized over a quadratic extension of K inside capital K. So any such group which is quasi-split but not split over K already is quasi-split and non-split over a little quadratic extension of degree 2, which is unramified. And so the affine root system is already visible in this degree 2 extension. And as I said, the affine root system has this diagram. And the symmetry means what? So when you take the symmetry, then rank is number of orbits in the new group, in the new diagram. So that tells you that the rank, so you see if the Galois group operates trivially, then the rank is, still n minus 1. But in case the diagram folds up, so folds up meaning the Galois group is operating, so it may be folding up, and depending on parity, you might have a vertex here or you may not, depending on the parity. So, this diagram just tells me that the Galois group is taking this to that, this to that, this to that. Which Galois group? This Galois group from capital K to small k, because this we have already taken care of in that board. So this Galois group is now operating, and it's telling you that there are just a few possibilities. Either the group was already quasi-split over the small field K, so that will be this situation, or the diagram here is acted upon by Galois group non-trivially, and in that case, the affine root diagram folds up, and then the possibility for rank, depending on the parity, is roughly half n. You know, I'm saying roughly because it depends on the parity. So the quasi-split group had rank n minus 1 because you had n minus 1 hyperbolic plane and norm form of a quadratic extension. But now, you know, the rank has gone down by half. So it's about half n. And what will tell you that? You know, quadratic forms over local fields tend to have very large rank. You know, they have large bit index because any form in 4 or more variable, more than 4 variable has a 0. So by using quadratic form, you cannot get this group because the rank is too small. If n is a million, the rank is about half a million, and rank can go down only by 2, you see. So you cannot get these groups. So which means that something mysterious has happened, and that's because after going down to small k, you need a quaternion division algebra to define your group. So that reduces the rank by about half. So the classification comes from such considerations, what kind of group you can expect to have over a small k. But this is not my job here, so I will not go into classification. I just wanted to say this because the buildings are good objects, but mathematicians should be happy just to know that buildings exist with certain nice properties. We really don't need picture of buildings because except for trees, we cannot draw anyone. Even in rank 2, you can draw an apartment, but not the building. So, I am happy just to know that there is a building. Yeah. Okay, so now let us begin our work. Okay, so, it keeps. Okay, so now, I want to prove some boundedness results first, just to warm up. Oh, this is going. No, that is. Okay. So let me prove three results. One is GK is bounded if and only if G is K anisotropic. Okay, so K anisotropic means that there is no split torus inside G. Second boundedness result is that given any bounded subgroup, of GK, it is contained in a maximal open bounded subgroup. And this is attributed, I think, by Bruhat to Langlands. But the proof which I will give you probably is not his proof, because I have not seen Langland's proof. So, and the third result is, so this first is attributed to Bruhat-Tits and Rousseau. Okay, and the third result is any, so I will assume that, let's assume for third GB a simple K group. And not just reductive, but semi-simple and simple, meaning it doesn't have factors other than 1. Okay, so GB a simple K group, then any unbounded open subgroup of GK contains a GK plus, that is the group generated by K rational elements of unipotent radicals of parabolic K subgroups. If you are in good characteristics, GK plus is just the group generated by unipotent elements, which may not be all of GK, but it's a slightly smaller group. Okay, so these three results come out from one single observation, and that is the following. So, I will state this as a So, first of all, there is a simple lemma, which I will leave as an exercise here. So, suppose X to Y is a finite morphism of algebraic varieties, affine algebraic varieties. Over K, then pi inverse B for B a bounded subset of YK bar is bounded. So inverse image of a bounded set is bounded. Of course, the image is always bounded of a bounded set. So this lemma, you should be able to prove it. Otherwise, in my paper, which will be a reference here, so that will be appearing soon in American Journal. So quite a bit of what I'm going to say will be simpler form of my results here in October 2019, so next couple of months. Okay, so this lemma is proved there. Now I will use this. Now the next proposition is, given a Zariski dense subgroup, say lambda of GK, Zariski dense unbounded. GK, and I will assume whenever I need that G is sitting inside GLV in terms of a faithful representation. Affine algebraic groups always can be embedded. So given a Zariski dense unbounded subgroup lambda of GK, there is an element lambda in lambda which has an eigenvalue greater than 1. In modulus, we have valuation, so you can take, a multiplicative norm or absolute value. So you fix number, some number less than 1, and raise to the power omega of that. And you see eigenvalues may not lie in over K, but it doesn't matter. We are working with henselian fields, so you have unique extension. Yeah, so this makes sense. Whenever you have an unbounded Zariski dense subgroup, you have such an element. And Zariski density is important because I can take unbounded unipotent subgroups in SL2 upper triangular group. So it's unbounded, but all elements have eigenvalue 1. So you see Zariski density is needed. Yeah, this lemma, this proposition is proved rather easily, but again, you can find that in the paper. By going to K bar, you see this V may not be irreducible, absolutely irreducible as a representation of G. You cannot take V to be Lie algebra, in general that's not faithful. And even if you took Lie algebra, Lie algebras tend to have invariant subspaces for even simple groups. But in any case, over K bar, you can find a Jordan-Holder series such that the successive quotients are absolutely irreducible, and then you can use Burnside argument. You remember Burnside's theorem says that if you have an absolutely irreducible representation of a group, then the algebra generated by it is the full matrix algebra. So that theorem, known as Burnside's theorem, the idea has to be used there. And it's elementary proof. So instead of going into the details, I will just state this as a proposition, and you can figure out a proof or look up my paper. Okay, now let us use this proposition to one by one prove the statements. So here, let's prove one. So suppose GK is bounded. Then it has to be anisotropic, yeah? Because if it's not anisotropic, a split torus will be K star, isomorphic to K star, and K star is a infinite, unbounded group. So the fact that GK is bounded immediately implies that it has to be anisotropic. Now we have to prove the converse, which is more difficult. So suppose you know that GK is anisotropic. Okay, and suppose it's unbounded. Yeah, so I'm offering the proof of first. So if GK, yeah, is unbounded, then you know, if you have read Borel's book, that GK is always Zariski dense in G for reductive groups. Yeah, you know, if you have a reductive group over an infinite field, and our fields are, you know, evaluates and so on. So over an infinite field, GK is always dense for reductive groups, and it's not true for other groups. So for reductive groups, it's true. So if GK is unbounded, then you know, because of Zariski density and my proposition on the other board, which I should pull up, okay, so because of that proposition, if GK is unbounded, it contains a G with eigenvalue, with an eigenvalue greater than 1. Okay? Yeah, that's what the proposition says. Now, you know, if you are in characteristic P, a power of G will be semisimple. Yeah? And the eigenvalue will be power, so it will still be 1, greater than 1. If you are in characteristic 0, you can take Jordan decomposition inside GK. You know, in characteristic P, you cannot take Jordan decomposition inside GK because the field may not be perfect. So in characteristic P, you just take power. In characteristic 0, just take the Jordan decomposition, which will be inside GK. And the semisimple part will have same eigenvalue as G. So in the upshot is, we can assume that G is semisimple. Yeah, by taking either Jordan's semisimple part or a power of G. And once it's semisimple, it can be embedded in a torus. You know, any semisimple element can be embedded in a torus defined over the base field. So G belongs to a torus, let's say T. And I will produce a character for T, making T to be isotropic. So, you know, since an eigenvalue, every eigenvalue is given by some character. So chi G, so there exists a character chi, but the problem is that this may not be defined over small k. But you know, there exists a chi defined over k bar, separable closure, such that chi G is greater than 1. And now you take the sum of Galois conjugates of chi. You know, this is defined over a finite k prime, finite separable extension. You take Galois conjugates of chi, add them together, and you get a character defined over the base field. And how do you know that it's non-trivial? So I have added characters, and most of the time when you add characters, you get 0. So what is the guarantee that you are getting a non-trivial character? See, the reason you are getting a non-trivial character is that the value taken by sigma chi on G is, you know, G is invariant under the Galois action. So it's just the value of chi G twisted by sigma. So this is evaluate this at G. So you are taking product of values of chi G, sigma chi on G. And each one is greater than 1 because Galois does not change the omega. There is a unique extension of omega to any extension. So in particular, Galois conjugation does not change the values. So when you take the conjugates, the product still is greater than 1. So the conjugates don't add up to 0. Okay, so this proves 1. Yeah, all of you think that it's correct proof. Okay, now what about 2? So now I have to prove, this is a theorem of Langland's allegedly. So let us try to prove it by this. Okay, so for 2, what you do is, given a bounded subgroup of GK, I want to first embed it in an open bounded subgroup. So how do I embed it? I take a lattice in V. Inside V, take a lattice. So lambda is now a different thing. So lambda a lattice, which means that it's a module over a ring of integers O, which tensored with the field gives you isomorphic thing to V. Okay, so lambda is a lattice. Now it may not be stable under the action of B. You remember my group is inside GLB, but this lattice may not be stable under the action of B, but what I will do is I will just apply B to lambda and add up over B. So that will be still a lattice because B is bounded. So I get a lattice here, which is now stable under the action of B. Yeah? And it's a bounded group, so the coefficients of lambda with respect to a basis, when you apply B, they don't increase too much. So, you still will be inside a bounded subset of V. So you will still get a lattice. Okay, so this is still a lattice, but it's now stable under B, and stabilizer of a lattice is an open subgroup, open bounded subgroup. So I can assume by this trick that B is open bounded. If it's not open, I do this trick. So it's open bounded. Now I want to use John's lemma. Actually, some of you may be allergic to axiom of choice, but maybe you can do it because it's all countable problems. Maybe you can do it directly. Okay, so using John's lemma, I want to say that this is contained in a maximal one, which means that if I have an increasing chain of open bounded subgroups, I must show that it gives me an open bounded subgroup in union. Yeah, so suppose I have BI increasing chain, I running over some countable or uncountable set. But it's increasing, you have indexing which is ordered set. So BI, so if union BI is unbounded, then you see each BI is Zariski dense. An open subgroup is always Zariski dense because the closure will contain an open subset of G. Yeah? Tangent space at identity will be whole Lie algebra. Okay, so each BI is Zariski dense, and the union therefore is Zariski dense, and this is unbounded, so it must contain an element whose eigenvalue is greater than 1 by that proposition. But that element has to lie in one of the BIs. So you will have problem, yeah, because BI are bounded, so no element in BI can have eigenvalue greater than 1. They all have eigenvalue of modulus 1. Okay, so this proves by Jean's lemma that union of bounded open sets or subgroups is bounded, and therefore you have maximal one. Okay, what about the third one? Third one says that if you have an unbounded open subgroup, then it contains GK plus. You know, this was a theorem of Tits, and he never published the proof. But you know, it's used sometimes. So since it comes out from my proposition, so I will offer a proof. So you see, the third one says that unbounded open subgroup contains GK plus. You know, it's an open subgroup, so it's Jarsky dense. And therefore, it contains an element of with eigenvalue greater than 1. And same in the Lie algebra. Yeah? Now, given an element G, you know how to define the parabolic subgroup PG. PG is set of elements which are under conjugation give you a limit. So PG is set of elements X such that GI X G minus I converge. That sequence converges, yeah. And U sub G, the unipotent radical here, is X such that GI XG minus I converge to 1. So this is a parabolic K subgroup, and this is the unipotent radical. So once you have found an element G which has eigenvalue greater than 1, then this parabolic is a smaller parabolic, and U sub G and UG inverse make sense. You can do the same thing with G inverse and PG inverse. So these are two opposite parabolics, and these are the corresponding unipotent radicals. And one knows by Bruhat decomposition that GK plus is generated by any two opposite unipotent radicals. So you are done. Yeah? Once you have found an element G, take the corresponding parabolic, and for G inverse, take the parabolic, and you are done. Okay, so now we will begin Bruhat-Tits theory. So, yeah. So, you know, one single proposition proves all these three theorems. So, I am really happy. Okay, now let us prove the following. So suppose you start with a group G, a reductive group, such that G prime, I will always denote by G prime the derived group, which means the commutator of G with itself. So such that G prime is anisotropic. Then GK contains a unique maximal bounded subgroup. And its description is following. So you have G in GK such that a chi-G lies in, a ring of big O. No, small O is, the multiplicative group of the ring of integers. In other words, the evaluation has to be 0. So chi-G lies in O cross for all chi in X star, the character group of characters defined over K. Yeah, so this is clear that any bounded subgroup will have to have only such elements, because bounded subgroup cannot have eigenvalue greater than 1. So character values have to be inside the multiplicative group of the ring of integers. So, but converse is true. That's what this theorem says, proposition. And so the idea is the following. So G has a maximal anisotropic connected normal subgroup. Unique, and that's obtained by going to G by G prime. G prime is already anisotropic, so you go to G modulo G prime and G, and let's call it pi. So this is torus now because I have divided it out by the derived group, so this is a torus. So this torus you can write as anisotropic times split. Yeah, from the structure theory of reductive groups, that the commutative reductive groups are tori. And so this G modulo G prime is a K torus, and any K torus has a unique decomposition as almost a direct product of a anisotropic torus and split torus, and you lift TA. So pi inverse TA is the unique maximal connected anisotropic subgroup. So let's call it, some name, H. Okay, and since this is anisotropic, HK is compact. But let's not hurry up. Now, you take maximal split central torus. Let S be the maximal K split central torus. Of G. Then we have so we have a decomposition of G as S times H. So G is S times H. Yeah, by construction, H is given by anisotropic part of the central torus. So, this is fine. But S intersection H, let's call it C, may not be trivial. So it's not a direct product, but almost direct product decomposition. And some of you who are more sophisticated, this intersection may not be smooth. So it may be a finite group scheme which you don't see. Okay, so but that doesn't bother us ever. So now you consider G mod C, and that is nothing but S mod C. Now it becomes direct product. You know, the offending thing you have divided out. So it becomes a direct product, yes?
You divide twice, S mod C and H mod C?
Yeah, because G already C is divided once. You see S and H intersect in G. So the diagonally sitting C has already been divided out to get G. Yeah? And therefore it looks, and I am dividing G again by C. So in other words, I am dividing by 2 copies of C. Yeah, you understand the point. You know, G already has the description of S times H, direct product, divided out by diagonally sitting C, because C is sitting in S as well as in H. So G mod C becomes direct product here. And you know, the map from G to G mod C is a finite map. And therefore, you can use that lemma which says that under finite map, inverse image of bounded is bounded. But now the description of bounded thing here is nice because it's a direct product. And for split torus, you know what bounded things are. You see the point to note here, and that's a subtle point, that C is a central group scheme. And so when you divide out by C, the rank does not change. You know, you take orthogonal group in 3 variables in characteristic 2, local field. And you go to symplectic group. Because you know, orthogonal group in odd number of variables can be mapped into symplectic group. Symplectic groups are always isotropic, even split. So from anisotropic orthogonal group to symplectic group, you have a map which increases the rank. But you know, this happens only because SO3 to SP2, the map has a kernel which is non-central. So non-central morphisms can increase rank. So you have to be careful in, you know, you are always careful, I know. So you have to be careful, but you know, we are careful here. So you know, these are central quotients. So this is anisotropic. Therefore, by the theorem, K points of this group is compact, and you know what is the bounded, and you know what is the bounded subgroup of a split torus. So you are done. Okay, so that is important. Now let us Bertrand constructed apartment. So I will do it in a different way. So we have now all the lemmas available to us which require to define apartments. Oh. Okay. My goodness. Okay. So now apartments, and here this will be very general, and then we will of course work with quasi-split groups to recover a Bertrand situation and then go on. Okay. So now our situation will be the following. S, a maximal K split torus in G. So we will fix that once and for all, and the general notation is centralizer of S in G will be denoted by ZS, and that's a reductive subgroup, connected reductive subgroup. And normalizer of S will be denoted by and as you know, NS by ZS is a constant finite group. So, you know, so the K rational point is nothing but okay, so that's a miracle, but it's true. Okay, so you have this, and most people call this to be a while group, relative while group, because I am working over any field, so it's a relative while group. Now, let's look at this extension, NS to W to 1, and the kernel is ZS. Yeah. Now let's look at ZS over K. Everything over K rational point. Now ZS is a reductive group, and its maximal split torus is S. And the derived group, therefore, is anisotropic. So ZS, the derived group of ZS, you know, center of ZS may be bigger than S, but we don't care. The derived group of ZS cannot be isotropic because that will increase the size of split torus. So I can apply the result that ZSK has a unique maximal bounded subgroup. Yeah? Because, you know, the derived group is anisotropic. And we proved that if the derived group is anisotropic, then the corresponding reductive group has a unique maximal bounded subgroup, and it had some description. So the unique maximal bounded subgroup of this, I will denote by just B for bounded. So I'm looking at this guy, you know, the unique maximal bounded subgroup, and I'm looking at the quotient. This is by uniqueness, it's a normal subgroup, so quotient is a group. And it contains the commutator, therefore this is an abelian group. And can you guess what this abelian group is? So I claim, let's now assume that the evaluation is discrete. I didn't assume it so far, but now first time I will assume that the evaluation is discrete. So, you know, the description of ZSKB was that each character takes value in the multiplicative group of ring of integers. So, the quotient, how do you measure it? You take the characters and take the evaluation of each basis of characters, and that's the isomorphism. You fix a basis of characters of ZSK, K characters, and you take, for each basis, you take the evaluation map, and that gives you a map into G, and there are R such characters, so you get a isomorphism with G to the power R, a copy of G to the power R, and that's the isomorphism. Note that characters of ZS sit inside characters of S, because you can take a character of ZS, restrict it to S, which is a subgroup. And since S is the largest central split torus, the character map, restriction map, is injective of same rank. So you see, S has dimension R, so the character group of ZS has rank R. Yeah. So this is, I will use this isomorphism. So let's divide out by ZSK bounded part. You see, because of uniqueness, not only this subgroup is normal here, but it's normal also here, because NS normalizes ZSK. So you can divide out by ZSKB, and you have still done nothing to finite while group W. But you know, this guy is G to the power R, and our apartment should be larger. It should be real numbers to the power R. So what I will do is, I will tensor this guy with R. So I will tensor that, and what will I get? That will be R to the power R. This is a Euclidean space. So what I am going to do is, I will embed this inside this, and I will always denote this group as Vs, because it depends on S. So, with tensored with R. So I get a inclusion, because G is included in R, I get this map. Now, this is an extension of W by G to the power R. And I have a map of G to the power R in R to the power R. So this extension, push out construction. So, you take the fiber product of this with that, and this copy you identify. Yeah, or some of you are more sophisticated. Think of it as a cohomology class with cohomology of W with coefficients here. And then you are changing the coefficients to Vs by inclusion. Yeah, this is given by H1 class, W with coefficients in G to the power R, and you are changing the coefficient by inclusion into a larger module. Huh?
H2 classes.
What is it?
Extensions are classified by H2 classes.
Yeah, H2, okay, yeah, sorry, H2. So you have H2 class, and then, So you are just, but this is more pedestrian, to just take the fiber product, a product of this with that, and identify two copies, here and here. So you will get the extension. Okay, now, miracle, W is a finite group with coefficients in Vs, which is a vector group, cohomology vanishes. So this extension, after this push out, always splits. But there is no uniqueness of splitting. So you have lots of splitting. So now I will replace the whole picture, I'm being. So now you have a Vs, and here I will have something which I will call E, an extension. And I have, as I said, the splittings. So, given an splitting here, you can let the group E act on splittings. So suppose phi is a splitting. You know what is splitting? Means a homomorphism, such that when you come back, you get identity. So any such extension splits, because this is vector space. So this extension splits. Let's take a splitting phi and call this map pi. So now I will act by elements of E. So E in E. So I will define E acting on phi to be the image of E conjugating W. Okay, so this is W is image of E conjugating W, so pi inverse, pi E inverse W pi E, and then you apply pi E back, So that's the action on splittings. And you can easily check that given one splitting, any other splitting is obtained by translating by an element of Vs. Okay, and if you are working with a semisimple group, this element is uniquely determined. So now the set of splittings of this short exact sequence is the affine space, which is the apartment coming from the split torus. Okay, and this has no base point because there is no God-given splitting. So this is an affine space which is in principle the underlying vector space is Vs, but there is no canonical splitting. So this is a affine space without a base point, and that's what the apartments are. Apartments are underlying space is Vs, but it has no base point. And now the group E acts on Vs. So E is this affine while group, if you like. And this acts on Vs, and this is the action which you use. So the normalizer of the split torus acts, and that it acts by affine transformation, as you can check. And moreover, so NSK acts by affine space of splittings, and ZS K acts by translations. Okay, this you can easily check. Just take a splitting and see what E can do to it. And you will, it's a concrete situation, and you will come up with the formula. So I want to give you the action of ZS on this, which we will probably use. So how does ZS act on it? Okay, so let's call it A, the affine space. So the space A of splittings, A is the affine space. So for any n in N Sk, the action on A is affine, and its derivative this is an affine action, so you can talk of its derivative at any point. So its derivative dn. So you see, this is an affine action on A, but A is a affine space under Vs. So its derivative dn is a map of Vs into itself. Yeah, the affine space, the tangent spaces are Vs, because it's just, affine space underlying vector space is Vs. So the tangent space at any point is Vs. And what is the derivative of this action? You see, Vs is the co-character group made into a vector space by tensoring with R. And N acts by, while group action. So Dn is just the while group. You see, pi goes into W, and so N goes into a while group element, and the while group element acts. So this you will check. Now, what is the translation action? So ZSK, so suppose I start with an element Z in ZSK. Then the translation of A by Z is by a vector V sub Z. And how do I determine this vector? It's a vector, it's translation, and the underlying vector space is. So what I will do is I will take characters. So you take a character chi g and apply omega, and for some reason you put a minus sign to make things, it's a convention. So you look at minus chi g. What does it do to a character? So a character is evaluated and then you apply omega. So it gives you in principle a co-character. And Vs is the co-character group tensored with R. You understand what I'm saying? For any character chi, I want to go to co-characters. You see, Vs is supposed to be the co-character group, tensored with R. So what is co-character group? It's the dual of the character group. So given a character chi, I should get a real number. For each Z in Z, I want to get a co-character value. So what I do is evaluate for a given G, I take the character value chi Z and evaluate using the valuation omega and put a negative sign. So I get a integer valued function on characters. For a fixed Z, I'm getting an integral valued function on the set of characters. So in other words, I'm getting a co-character. And that's the co-character which gives you the translation. So Vz is co-character which applied to chi gives you this number. So that's the definition. Okay, and this you will verify. Now, in my remaining time, let me say the following. Now, you see, abstractly, I have defined an apartment. And this definition is adequate for, split groups and quasi-split groups because, this works very well. Now, this definition is more general. I can take any split torus, maximal split torus. I can take normalizer by, the usual Borel-Tits theory. But the problem with this description of apartment is the following. Suppose I start with the building, which thanks to Bertrand we have building of GK. You know, when I go to large field extension, you know, my residue field was assumed to be perfect. So when I go to maximal unramified extension, the residue field is algebraic closure. Now, this is a theorem of Steinberg that if you have a evaluated field whose residue field is algebraically closed, then groups are quasi-split. You know, this was a conjecture of Sayre, and Steinberg in a famous paper proved it. So, you know, if the field is, residue field is imperfect, you don't have a replacement. So, in my paper, I have to assume that somehow Bruhat-Tits theory is available over capital K, because I'm not assuming that the residue field is perfect. So by hook or crook, you have to have Bruhat-Tits theory over capital K, and then descent mechanism works. So whenever you have Bruhat-Tits theory, by magic or by any other means, you can descend. Now, if the residue field is perfect, then going to maximal unramified extension makes the group quasi-split. And then you have Bruhat-Tits theory thanks to Bertrand. You know, he showed that there is Bruhat-Tits theory. So you can descend. So now the problem is descend, as we will show, this building, when I take the Galois group of K over K, the fixed points give you a set which is convex, and I will show you that it has all the properties which buildings should have. But what about apartment? So if I abstractly take his apartment, in other words, in the building here, then of course the apartment has this nice description. But what is the guarantee that the fixed point of this apartment will give me apartment there? Because, you know, these apartments may not even be gamma stable a priori, because your torus you started with may not be defined over the base field and so on. And even if it's defined over the base field, what is the guarantee that this gives you the apartment with the right properties? So that's the difficulty. So the difficulty is, even though you have everything over capital K, in descent, you have to produce all apartments, and you have to produce polysimplicial structure satisfying certain axioms which he wrote down, B1, B2, B3, whatsoever were axioms. And the first difficulty already is, you know, what are the apartments? You know, in principle, apartments should look like what I described. But you see, it's not the abstract definition. I have to sit inside, you know, with that definition, how to embed apartments in this big building. You see, this comes with apartments. And when I take gamma fixed points, I have to build apartments, which should be, of course, like that, but sitting inside. So we will continue this, but you know, what I will make use of all the time is some results on group schemes. And these results are very, very minimal. In fact, the only results which I will use are 2 or 3 from SGA. And I will summarize those results. You can take them at face value, but at his website, you can freely download all the chapters of SGA 3, nicely typed. So, you know, you have easy reference, and I will use nothing very sophisticated. So the interesting thing is that you can do descent without any sophisticated machinery. And the only theorems which I will need is use of Hensel's lemma and variety of tori and so on inside a scheme. So, you know, from next time we will do this. And finally, I want to say that there was a work of my colleague JKU and myself where we considered also finite group actions. So if you have a group, reductive group, given with finite group of automorphisms. So G is a reductive group and a finite group of automorphisms. So these are algebraic automorphisms of G. And then you can look at G theta, the fixed points under automorphisms, and may not be connected, so take the identity component. So if order of theta is coprime to the residue field characteristic, so P should not divide the order, then this group is reductive. And the question is, because of Bourbaki transport the structure, the theta acts on the group, therefore on the building, because transport the structure. So what is with theta fixed points here? And it turns out that the theta fixed points is a building, but with a very different simplicial structure. So the simplicage in the unramified case are intersection of simplicage of the big building with the smaller building. But in case of this theta action, the simplicage are very different in general from the original simplicage. But in any case, we proved that this is a building and Bruhat-Tits building of this reductive group. So fixed point of the G under theta give you a reductive group, and its building is just the fixed point building. And this allows you to make tamely ramified descent, because in tamely ramified extension, the Galois group is of order prime to P by definition. And then you take restriction of a scalar, and theta Galois group will act, and then the fixed point. So you recover Rousseau's theorem, for example, from this. So anyway, if time permits, I will go into that also. And we can construct group schemes and everything there too. So that's a second paper which will appear next year. So we redo what I did with JKU. You know, there we didn't show the simplicial structure and so on, and we didn't construct the group schemes, and we didn't work with possibly imperfect residue fields. So all that is now taken care of my new paper. Okay, so I will stop here.